Welcome to Talk Tensors, the deep dive, where we get into the weeds of some really fascinating machine learning research.
That's right. And today we're looking at a paper that definitely made us pause and think.
Yeah, it's called Decoder-Only LMs Fail to Solve This Elementary Task Above 1D Chance Due to a Learned Shortcut That Absorbs Training Supervision. Quite a title. It's by Bachmann and Nagarajan from 2024.
And it hits on something pretty counterintuitive. You have these powerful language models, decoder-only ones.
The standard kind we use a lot.
Exactly. And they fail quite badly, actually, on a graph search task that looks, well, pretty simple on the surface, the PathStar task.
Which is weird, right? Because you think pathfinding, planning, that's something we want these models to do.
Precisely. And this failure, it really forces you to question the standard way we train them next token prediction. Is it actually enough?
Okay, so that's our mission for this deep dive then. We want to unpack why this simple task trips up these models.
Understand the explanations the authors propose, see what fixes they tried.
And figure out what it all means for, how we build and train LMs going forward. We want to give you, the listener, the key insights without you having to wade through everything yourself.
So let's start with this task, the PathStar task. Can you paint a picture?
Sure. Imagine like a central dot that's your start node, S.
Okay.
And radiating out from it are these spokes or arms. Let's say there are D arms, and each arm has M steps or nodes along it.
Right, like a starburst. All arms the same length.
Exactly. Now, the model doesn't see this nice picture. It gets a jumbled up list of all the connections, like node A connects to node B, node C connects to node D, and so on. Totally shuffled.
So no obvious order to the connections it sees.
None at all. And then it gets a query. Okay, find the path from the centers out to a specific target node T at the end of one of those arms.
And it has all the edges, all the connections just shuffled.
Right. You'd think, okay, piece it together, but that's where the surprise comes in.
Yeah, the big finding. These standard decoder-only models, trained with teacher forcing.
Which is the normal way, right? Where you feed it the correct previous token during training.
Exactly that way. They basically can't solve it. Their accuracy is stuck around 1 divided by D, the number of arms.
So random guessing. If there are 10 arms, it gets it right 1 out of 10 times.
Pretty much. Which is kind of shocking for these sophisticated models. It really makes you wonder about next token prediction for anything needing planning.
So a key point for listeners right away. This simple failure suggests maybe our standard training methods are actually stopping the model from learning to plan properly, at least for this kind of task.
That seems to be the implication. It's not just about planning ability, but how the training itself shapes what's learned.
Okay, so let's really get into the task details. Star graph, D arms, M lengths.
Model sees shuffle edges, UV, WX, etc., gets the query, ST, has to output the sequence of nodes from S to T.
And the paper highlights that the really hard part is that first step out of S, right? Picking the right initial direction.
That's the crux of it, supposedly. Choosing the correct leading node, the first node on the target arm. Once you have that,
the rest is just following the chain.
Yeah, in theory. You just look up the next connection. So the challenge seems concentrated in that initial planning move, which makes the failure even more puzzling.
And again, the big result, standard models fail, stuck at 1D chance. Even though, as other work showed, they can technically represent the answer.
Right. It's not a capacity issue. They could express the path. The problem is learning to generate it reliably with teacher forcing.
It really casts doubt on just using next token prediction if you want structured reasoning or planning.
And the implications are pretty significant. We use LMs for all sorts of complex stuff now.
Stuff that definitely needs planning.
Exactly. So if they stumble on this minimal, stripped-down planning task, what does that mean for harder problems? The authors designed this task specifically to isolate potential weaknesses.
Like a stress test for the training method.
A very effective one, it seems. And it's not like people haven't noticed potential issues here before. Some researchers even proposed totally new architectures to try and fix this kind of planning deficit.
But this paper suggests maybe the architecture isn't the main problem.
That's their angle, yeah. They're pointing the finger more at the training paradigm itself, the next token prediction with teacher forcing.
Okay, so let's zero in on that. Standard training, teacher forcing. Why would that cause this failure? What's the mechanism?
This is where they bring in the idea of the common hidden component, the CHC. It's essentially a shortcut the model learns.
A shortcut? How does that work?
Well, because of teacher forcing, during training, the model always gets the correct previous word or token as input to predict the next one.
Right. Giving it a hint.
A very strong hint. So the model figures out, hey, often I just need to predict the very next node based on the one I was just given. For the PathStar task, this means once it predicts that first node after as.
Even if it guesses it wrong.
Often, yeah. After that first guess, for all the other nodes in the arm, it learns it can just find the edge starting with the previous correct node, which it gets via teacher forcing. It becomes a simple lookup.
Ah, so it doesn't need to think about the whole path, just the immediate next step using the answer key.
Precisely. They call this excessive supervision. It lets the model bypass the actual path reconstruction. The only part that requires any real pathfinding effort is choosing that very first leading node.
So the model learns a cheap trick instead of the actual skill. That makes sense. It's optimizing for the training setup, not the underlying task logic.
Exactly. All the useful sequential info gets funneled into learning this single-edge lookup trick, the CHC. It never learns the algorithm to find the path from scratch.
Okay. And the paper was specific about how the input looked, the tokenization. Can you break that down?
Sure. The query, like start ends and target T, gets special markers, maybe CSEE. Each connection edge UV is tokenized like UV with a separator. Then the full input is query tokens, then all the UV edge tokens completely shuffled together, and finally maybe an end marker like.
And the shuffling is key because it breaks any natural order.
Crucial. It forces the model to rely on the actual connections, not just the sequence they're presented in. The target it has to predict is just the nodes in the correct path, RT. And that RT is what's used for teacher forcing.
They also mentioned training from scratch on fixed size graphs, right? Fixed D and M. Why do that?
Good point. That was to keep things clean. If the graph size changed all the time, a failure might just mean the model struggles to generalize to different sizes.
Controlling variables.
Exactly. By keeping D and M constant, they could be more sure the failure was about the task and training method itself, not just generalization or pre-training knowledge. They wanted a clean slate.
And they addressed earlier concerns about maybe the model just memorizing weird patterns in the data.
Yeah, there was this idea that maybe with enough examples, the model finds spurious correlations. So these authors used an online data set. They generated new graphs on the fly during training instead of using one big fixed set. This makes it much harder for the model to just memorize specific examples. They also simplified things a bit by matching the node vocabulary size to the graph size.
Did that help?
It helped reduce the chance of simple memorization, yeah. But importantly, even with this setup, the task still wasn't learnable by the standard models.
So it wasn't just about memorizing noise in the data.
Seems not. It reinforced their idea about this training shortcut, the CHC being the real culprit.
Which leads to this concept you mentioned, supervision adulteration. That sounds serious. What does it mean beyond just overfitting?
It's a really central idea for them. They argue the CHC isn't just regular overfitting. It's a direct result of how we supervise. The teacher forcing, providing the previous correct token, that's the main adulterant.
Okay.
It enables that trivial lookup, but they take it further. Even how we set up the task is a form of supervision. Shuffling the edges randomly, that's a choice. Putting the query first, that's a choice.
Huh. I never thought of task setup as supervision.
Right. Even training on fixed-size graphs, they argue, could be seen as a subtle form of supervision, nudging the model in a certain direction compared to training on varied sizes. It's about how the entire training environment might inadvertently provide these shortcuts.
That's a really different perspective, that our design choices are implicitly teaching the model how to solve it, potentially in a shallow way. And they had that experiment with causal-wise shuffling.
Yes, that was super interesting. In that version, if edges U, V, and VW were on the same path, they kept them in that order in the input list.
So preserving the local path structure.
Exactly. And guess what?
The models learned it.
Yep. The task became learnable. This strongly suggests that breaking that causal chain with the random shuffling, combined with the teacher forcing shortcut, is really what makes the original task so hard. The model can exploit local links without needing the global picture.
Wow. Okay, so the problem is clear. Adulterated supervision CHC shortcut model doesn't learn the real task. What did they try then to fix it, to break that shortcut?
They explored quite a few interesting directions. First up was token masking.
Masking, like hiding parts of the input.
Kind of, but on the target side during training, the idea was to stop the model from always getting the perfect previous token from teacher forcing, break its reliance on that shortcut.
How? Just delete some tokens sometimes.
Basically, yeah. They tried randomly dropping out some of the target tokens it would normally see as input, or sometimes replacing them with random other tokens. Introduce some noise, some uncertainty.
Make it work a bit harder.
Right. Force it to look beyond just the immediately preceding token, maybe engage more in that recursive reconstruction of the path.
And did it work?
It did. Token masking made the PathStar task learnable. They noted some potential scaling issues, but fundamentally disrupting that perfect teacher-forcing input helped break the CHC.
Interesting. What else? Did they try changing the prediction goal itself?
They did. That falls under alternative sequential distributions. Instead of just predicting the single next token, try to predict something richer about the future.
Okay, like what?
Well, first, they tried a bag-of-words approach. At each step, the model tries to predict the whole set of remaining tokens in the target path, art, but without worrying about the order yet.
Just knowing which nodes are coming up eventually?
Yeah. And that actually had some success. It suggests just knowing the future components is useful.
But order matters in a path.
It does. So next they tried label smoothing, but with a twist. They weighted the loss, so predicting near future tokens correctly mattered more than predicting far future ones.
Trying to enforce sequence.
Mm-hmm.
Did that work better?
Not really, apparently. The weighting kind of messed with the loss scaling in unhelpful ways.
So what was the winner in this category?
That seemed to be ranking into the future, or RITF. This was clever. Instead of predicting probabilities, it learns to rank tokens.
Rank them how?
It learns two things. First, rank the correct future tokens in the path R higher than any incorrect tokens. Second, rank the tokens within R in their correct sequence.
So compare and compares the tokens. This one comes before that one. This one is right. That one is wrong.
Exactly. A much denser, more structured signal about the future sequence. And RITF performs significantly better than bag of words or the weighted label smoothing.
That makes sense. Giving it more structured feedback on the sequence. What about scratch pads? I've heard of those. Using intermediate steps.
Yeah, the idea is to have the model predict some intermediate stuff before the final answer, giving you another place to add supervision. Help it break the problem down.
What kind of scratch pads did they try here?
They considered simple ones, like maybe predicting the path in reverse, but they figured that could probably be learned by the same old CHC shortcut, so not very insightful.
Right, wouldn't solve the core issue.
So they focused on graph reconstruction scratch pads, GRSP. Here, the model had to predict pairs of nodes, the leading node of an arm and the target node at the end of that same arm.
Identifying the start and end of each potential path.
Essentially, yeah. And then these pairs were given in a sorted list, maybe sorted by the leading node or the target node. The hope was if the model can explicitly identify the arms, maybe that helps it reconstruct the path.
Seems logical. Did it help?
This is where things got really interesting and surprising. The answer was mostly no.
No. Even identifying the arms didn't help.
The models got good at predicting and sorting these leading target pairs. They knew which arm they were supposed to reconstruct, but they still couldn't reliably generate the intermediate nodes of the path.
Wait, so they knew the start and end but couldn't fill in the middle?
Exactly. Which led the authors to suspect that the real difficulty might not even be the initial planning, choosing the leading node, but the seemingly simple step of actually following the path given the shuffled edges. Graph reconstruction under these causal constraints.
That flips the script a bit, doesn't it?
Yeah.
We thought the planning was the hard part.
It really does. It suggests the deterministic path following is harder for the model in this setup than we might assume.
Wow, okay. Did they try changing the queries? You mentioned general queries.
Yes. So originally the queries always go from start as to the very end t. With general queries during training, they'd sometimes ask for the path from hes to an intermediate node along the correct arm RT, not just the final one.
Asking for subpaths.
Exactly. Though at test time, they still only asked for the full path to the end.
And did training on these subproblems help?
It did. It made the task learnable and actually worked better than using just a fixed subset of intermediate nodes. The idea is that this forces the model to decompose the task.
Learn how to find path segments, which helps it learn the whole path.
That's the hypothesis. Breaking it down into smaller, overlapping problems induces task decomposition.
Okay, that makes sense. What about changing the graph itself? The tree star.
Right. They tried tweaking the topology. Instead of simple arms, maybe the arms themselves had some branching, like a tree, but all still coming from es. The idea was maybe this more complex structure would naturally disrupt the CHC shortcut.
Make the simple lookup less effective.
Potentially, yeah. Trying to foil the shortcut by changing the environment.
And lastly, varying the graph size during training.
Yes, generalized length decomposition instead of fixed D arms and M length.
Mix it up.
Exactly. Train on graphs with varying D and M sampled from a range. This stops the model from learning tricks based on a fixed size, like knowing the path is always M steps long.
Force it to learn a more general strategy.
Precisely. And this also worked, making the task learnable, combining this variable size training with the general target queries. That gave even better results.
So pushing the model towards generalization and task decomposition seems key.
It really seems that way. Anything that prevents reliance on fixed properties or simple lookups and encourages breaking the problem down.
Okay, so stepping back from the specific solutions, what are the bigger picture, maybe novel ideas or implications this paper brings to the table, especially for understanding graph tasks on transformers?
I think the biggest one is reframing the core difficulty, moving from it's a planning problem to it's actually a graph reconstruction problem under causal constraints.
That the bottleneck isn't deciding where to go first, but actually following the path once you've decided, given the shuffled input.
That seems to be their strong conclusion, yeah. Which is, frankly, quite surprising. It suggests that deterministic procedures can be unexpectedly hard for these models, depending on how the information is presented.
So future work could look at how to make that reconstruction easier. Different input formats, maybe.
Exactly. Or maybe training objectives better suited to causal reasoning from shuffled data. And they also raise the point about semantics. This task is deliberately abstract, just nodes and edges.
Right, no meaning.
How would adding real-world meaning or features to the nodes and edges change things? Would that help or hinder? It's an open question about how semantics interacts with this kind of structural learning.
And the whole idea of task decomposition seems critical.
Absolutely. Why is breaking the problem down so necessary here? Answering that could tell us something fundamental about how transformers learn sequential recursive tasks like graph traversal, and this idea of adulterated supervision.
Yeah, that feels important.
It's broader than just this task. They hint we should look for this elsewhere. Are there other tasks where standard training methods might be teaching shortcuts, preventing deeper learning? They mention a counting example from other research.
So we might be fooling ourselves in other areas too.
It's a possibility we need to consider. Are we just teaching models to pass the test or to actually understand the process?
Okay, so let's try and wrap this up. What's the final crystallized takeaway from this deep dive?
I think the main message is, don't panic about decoder-only models being fundamentally incapable of planning based just on this result. The failure on the original PathStar task looks like an artifact.
An artifact of the specific training setup.
Yes, specifically the adulterated supervision from teacher forcing combined with the shuffled input, which allows that CHC shortcut and hinders task decomposition and graph reconstruction. It's not necessarily a failure of next token prediction for planning in general.
So the task itself is kind of fragile, sensitive to these setup details.
Extremely fragile, it seems. Small changes to the input, the queries, the training variants, they can flip it from impossible to learnable.
Which, as you said, might be good news for more complex, real-world tasks.
Possibly. Those tasks might have enough inherent complexity or variability that these specific shortcut failure modes are less likely to dominate. The model might be forced to learn more robust strategies anyway.
So, for everyone listening, the call to action is maybe to think more critically about our training setups. Are we creating unintended shortcuts?
Definitely. Consider task decomposition. Think about how supervision might be subtly adulterated. It's worth digging into the Bachmann and Nagarajan paper if this sparks your interest. These concepts could apply way beyond just graph search.
Absolutely. Food for thought. Well, thanks for joining us for this deep dive on Talk Tensors.
Always a pleasure.
Join us next time as we tackle another piece of the puzzle in the ever-evolving world of machine learning.